All right, great. So yeah, welcome to the webinar. I'm happy to introduce Xiangyu Gao, who is actually a first-year PhD student with Anirudh Sivaraman and working with me. So he's at NYU, finished his master's from NYU as well, and he's actually really interested in programmable switches and languages for programmable switches and program synthesis and kind of applying sort of program synthesis in domain-specific ways in this domain. So, okay, so I'll let Xiangyu take it from there. I think he's going to tell us about some self-proclaimed interesting work. It's also my work. So he's going to tell us about some really interesting work on generating packet processing code for programmable switches using synthesis. Okay, you take it from there, Xiangyu.
Okay, so thanks, NG. So I'm Xiangyu, and I'm advised by Srinivas Narayana and Anirudh Sivaraman. So today I will present our work of auto-generating fast packet processing code using program synthesis. So this is joint work with Tegan Atish, Anirudh from NYU and Srinivas from Rutgers. So just give you some background introduction. Recently, programmable network devices have become quite widespread because they are more flexible than fixed function ones. And they also run at a fairly high speed today. So for example, programmable switches like Tofino run at 6.5 terabits per second. SmartNIC run at 40 to 100 gigabits per second. And the net FPGA platform run at 40 gigabits per second. So it is very easy to get started with programming these devices. For example, you can attend a workshop or you can read a tutorial. However, developing fast packet processing programs for these substrates that fit within resource constraints is really hard. So today there are two main approaches to write these fast programs, but none of them is easy to implement. So first for handcraft, we can handcraft the programs, but it requires manual optimization by experts who are familiar with almost every underlying hardware architecture. For example, they must be aware of the cache and memory hierarchy for CPUs and SmartNICs, and they must be aware of the arithmetic logic unit or ALUs for switches, or lookup table of an FPGA platform. For instance, Microsoft had a dedicated team of hardware engineers to program its FPGA-based SmartNIC. So the second approach is to rely on the compiler itself to let compiler do code generation automatically. A compiler will definitely elevate the difficulties of generating such code, but building the compiler itself is arduous because it requires significant engineering efforts, which is both time-consuming and money-consuming. For instance, Intel, AMD, ARM, they all have large compiler teams to develop compilers for each of their hardware architecture. In addition, because of the evolving nature of the hardware architecture, which means hardware architecture is unique, sometimes it's hard for us to find such a team for newly emerging packet processing hardware. So hopefully I have convinced you like writing and compiling fast programs is not that easy. So let's look at a very simple example that illustrate how tricky it can be to write fast packet processing programs for these substrates. For packet processing substrates like switches, compiler have an all or nothing characteristic, which means it will either fit the program into the hardware or reject it as being too expressive for the hardware. Consider an example from Domino programming language for program packet processing code. So I will talk about Domino in more details later, but for now, it is sufficient to think of it as a C# language and automatically compile it into a hardware configuration for programmable switches. So the compiler will automatically find which opcode to use and which ALU input to use and configure the hardware muxes. So what could go wrong with this setup? Today's compiler will produce different outcomes on semantically equivalent programs. So let's look at a real example from Domino. Let's say if you want a program that sets an indicator variable for the first packet, you could write it in this way, right? However, Domino compiler will fail to find a hardware configuration to implement it. But if you rewrite it into this version, which is semantically equivalent, now Domino can find it because Domino's compiler's heuristics are not intelligent enough to realize that these two programs are actually the same. While you can develop specific compiler algorithm to fix this particular issue, this is still a problem that crops up in other scenarios and even happen with commercial people compilers as well, where a slight semantic preserving modification to your code can cause a completely different compilation result without any particular good explanation. So in response to above concerns, our proposal is to use the field of program synthesis to develop code generator for packet processing code. At a really high level, program synthesis is the process to automatically generate a program that satisfies a specification. A program synthesis engine takes two inputs. The first one is the search space represented by one partial program, and the second one is the specification. So then, program synthesis engine will use an exhaustive search algorithm to find the completed program that satisfies the specification or return infeasible if none exist. To be specific, we can use search space of partial programs to represent the machine code skeleton and use specification to represent the high-level language program. The program synthesis tool we use in our project is Sketch. So in a sense, our main idea is to use program synthesis as an enabling technology for rapidly building compiler for emerging packet processing hardwares. So now I will give you a brief tutorial on how Sketch synthesis algorithm works. And Sketch actually use a counterexample guided inductive synthesis, or we call it CEGIS. The program synthesis problem solves the whole values in the formula in first order logic, which is a quantified Boolean formula, or QBF problem, even harder than set problem. So therefore, to simplify this, CEGIS divides the whole program synthesis problem into two phases. So the first phase is synthesis phase, and the second phase is the verification phase. And both of them are simpler than directly solve the QBF problem because each step we either fix the test input or whole values, which will turn the QBF problem into a set problem, and then you can leverage some efficient set solvers to do this. The synthesis phase will try to solve the whole value assignment to satisfy the partial inputs, and the verification phase will verify the whole value assignments on all input, which is specified by programmers. For example, we can set the input range to 5-bit. In the beginning, Sketch will randomly choose a subset of all input to do the synthesis. If it fails, it means there should be no feasible solution because we cannot find a feasible solution even for the subset, let alone for all the input space. So if it gets success, it will continue to the verification phase to test more inputs. If we pass the verification, which means we are lucky enough to find the final solution, which means the solution satisfy the partial input can also work for all other inputs. Otherwise, there is at least one test case making the current test fail to work. So we add this counterexample to the input set and repeat synthesis again, back and forth until we get the final result, which means either success or failed. So let's see a concrete example for Sketch. For example, the specification is a function that adds its input to itself 3 times. Here is a partial program, and we supply to Sketch. And the question mark here represents an unknown constant called whole. Now Sketch can find a whole assignment for this partial program and complete the program by setting the whole to 3. So on the other hand, if we consider another partial program, Sketch cannot find a whole assignment for it. And then we say it is infeasible. So let's say why synthesis will be a suitable tool for code generation in the context of packet processing. First, for fast packet processing code, there's always a lot of value in finding high quality code using the exhaustive search algorithm used by program synthesis. Now, what do we mean by high quality? Here are some example metrics that we could use to define the quality of the generated code. For RMT and PISA style pipeline architecture, It could be the latency consumed by packets as they go through the pipeline. For NPU-style processor architectures, it could be the throughput that can be achieved by a certain packet processing programs. So in such case, we believe that synthesizers might be able to discover high-quality assembly implementation of packet processing programs with significantly lower engineering effort relative to handcrafted compiler rules for translating programs into machine code. However, program synthesis is not the perfect thing. There is no free lunch. Program synthesis will face a key challenge. It can be very time-consuming to solve because the search space might be very large, and the spec that satisfies the implementation may be hiding in a very small area. This is similar to like you want to find a needle out of a huge haystack. You have to use magnifying glasses to find it. However, it is still meaningful to use program synthesis for packet processing, mainly because of two reasons. The first one is we can leverage domain structure that is unique for fast packet processing. For instance, most fast packet processing programs are naturally very small and simple. As an example, if you think of some congestion controls algorithms like RCP or an AQM scheme like BLUE, it only takes a few lines of pseudocode. Similarly, if you look at a packet processing language like P4, there are no pointers or loops inside because these can ensure the deterministic line rate performance. Also, packet processing programs don't change that often, so long program synthesis time will not that as much of a concern because usually the frequency of the code generation is low. So the second reason has to do with the improvement in program synthesis technology over the last 15 years. Currently, there are several mature open source synthesis tools such as Sketch, which we use in our project, and Rosette, and some other promising real-world applications of synthesis. So this is also an active area of programming language community. Since 2014, there has also been a yearly programmer synthesis competition that will compare different algorithms for program synthesis. So every year we could borrow a lot of new updated tools through this competition. So because of the benefits using program synthesis to generate fast packet processing code, we plan to implement Sketch to do code generation for programmable switches. And I will briefly describe the whole process. Suppose we have two people. The first one is a programmer, and the second one is a compiler developer. So at a high level, the programmer writes the packet processing program in Domino, which we can then convert into a Sketch specification. The compiler developer will express the capability of a simulator of the protocol independent switch architecture, or PISA. Then both of them will be parsed into the Sketch program synthesis engine. Finally, when Sketch output a completed program, it is converted into a machine code for the PISA simulator. So we call this whole system Chipmunk. Now, let's look at Chipmunk in more details. Our specification for Chipmunk is a program that is expressed as a packet transaction in the Domino programming language. The reason we picked Domino is that it has a relative high-level programming model that with transactional semantics, which means as far as the programmer is concerned, the packet executes from the top to the bottom in the programmer's packet processing code as if there were no other packets in the system. We can also use atomic structure by the P416 to express this packet transaction and plan to support this in the future. The programmer can use state variables such as count to represent persistent switch state and packet fields such as packet.sample to represent fields in packet header. So what about the partial program for Sketch? We consider a simplified version of the PISA match action pipeline. We abstract the effect of these actions on a packet into a two-dimensional grid of ARUs. We have two types of ARUs. Stateless ARU that only manipulate the packet headers, and the stateful ARU that will manipulate both persistent switch state and packet headers. So we use PHP containers to represent the storage for the packet headers as they move through the switch pipeline. And the compiler writer will also specify how ARU use input marks to choose PHP containers as the input operand. And she will also specify how PHP containers use output marks to choose from the ARU outputs. So each stage will share the same structure. The compiler developer will use hosts to specify what operations is carried by each ARU and the value of the immediate operand to use and which packet headers are used for a particular ARU, which means it will specify the total functionality of the programmable switches. And then they are converted into a sketch partial program. Now, once we have the specification and partial program in hand, we'll feed them into the Chipmunk. We can then use the output from the sketch to generate the machine code for the PISA simulator. So how do we evaluate the Chipmunk? First, what should the baseline be? Actually, we compare Chipmunk against the Domino's existing compiler because this compiler uses handcrafted rules for translating Domino program into machine code for the simulator. For alternatives, we also consider using some commercial compilers from chip vendors such as Barefoot. But these compilers don't yet support high-level transaction programming models that programmers use in Chipmunk. We also consider some open source P4C compilers, but the open source compiler currently only support the software targets such as eBPF and the behavior model. So we compare Domino and Chipmunk in two metrics. One important difference between the PISA simulator and the traditional CPU is that, what I also mentioned before, is that in PISA model, compiled program either run at full line rate of the switch or are rejected by the compiler, which means they have all or nothing characteristic. So the first metric for the comparison is the compilation result, which is whether Domino or Chipmunk even successfully compile a given program. So the second metric is the amount of resources consumed by Domino or Chipmunk if they both compile a given program. So for benchmarks, we pick most of the benchmarks from multiple resources. However, we cannot directly use them because we have also already confirmed that they will get successfully compiled by Domino, and we also ensure that they will compiled successfully with Chipmunk too, which means if we directly compare them, there will be not much difference between Domino and Chipmunk. So we already asked this question. If we mutate these programs in semantically preserving ways, like what I showed before, will Domino and Chipmunk still successfully compile them? So theoretically, the answer is yes, because if one program gets compiled, the semantically equivalent mutation should also get the same result. But empirically, it totally depends on how good Domino and Chipmunk are in finding this machine code to implement a particular high-level packet processing program within a limited period of time. So let's see how Domino and Chipmunk perform in these programs. So we can see Domino failed to generate code for most of these mutations of original programs because it incorrectly concluded that these programs are too complicated to fit within the capacity of the underlying hardware. By contrast, Chipmunk compiled most of these mutations, or even all of these mutations, because it searched more exhaustively for any means of implementing the program use the hardware capability. So if we look at the compilation time of Domino and Chipmunk, this is the main drawback of Chipmunk, or we can say it is the Achilles heel of Chipmunk. Well, Domino's compilation time are on the order of several seconds on most mutations, but Chipmunk takes several minutes. The worst case is around 2 hours for some of the mutation. So we are currently working on some algorithms to reduce the Chipmunk's compilation time. For mutations, where both Domino and Chipmunk are successful, Chipmunk can use fewer resources. It will use fewer pipeline stages, which is more constrained in the programmable switches, because most of the programmable switches only have around 10 stages. Sometimes Chipmunk may consume more ARUs per stage than Domino, but given that there are hundreds of ALUs available per stage in most of the programmable switches. This is not a huge problem. So to conclude, Chipmunk transplants the program synthesis idea to networking to automatically generate fast packet processing code. And more generally, we also think program synthesis can help a lot of things, such as enable fast packet processing in the same way that SET and SMT solver have helped in enabling network verification over the last decade. So as a part of future work, we plan to explore code generation for other programmable substrates like SmartNIC, FPGA, and the DPDK framework. Thank you for listening. I'm happy to take any questions.
Thank you, Xiangyu. I think we have a good amount of time for questions. So I guess people could just unmute themselves and ask questions if you're available.
Yeah.
Hello, can you hear me? This is hello.
Yeah, I can hear you.
Yeah, this is Anand from Alibaba Group. I'm leading the verification and synthesis projects here.
Okay.
Okay. Yeah, this is interesting question. Very interesting thing. So yeah, I need to clarify some of my understanding just to make sure whether I understand this correctly.
Sure.
The first thing is it seems as though the compiled programs can run successfully on the PISA simulator.
Yes,
Did you try the real hardware, for example, the Tofino 1, Tofino 2, or some, the chips?
Yeah, we now we have some benchmarks. I mean, all these benchmarks show here. I mean, 10 out of these 14 can successfully running on Tofino already. This is our current. We updated the results. This is our latest result. And 4 of them failed to work, which is highly possible is because the current Tofino ALU is not that expressive enough to support some functionalities of some of these benchmarks. But we have already verified a lot of cases have already successfully running Tofino.
Okay. I see. So it seems the all the algorithms in this table should be the benchmarks you tested. By the way, so in HowNets last year, I remember there's another approach named the Deja Vu. They try to put the SoC chain into one ASIC. I'm not sure whether you remember that work. It should be in the same session, right? With your paper. Did you try that one? For example, have a SoC chain including firewall, gateway, a lot of algorithms in the SoC chain. It's very difficult to put the entire thing in, into the say Tofino or something. Did you try that? See whether your synthesis algorithm.
Yeah, this is a good question. I also heard his talk in HotNets last year, and I guess we have now we only support one chain. We didn't support multiple chains right now. I guess maybe for future we will also try his method in our part too. Yeah.
I see. Yeah, another small question. Yeah, I read the Domino paper multiple years ago, but I cannot remember all the details. But the question is about the language. So it seems the high-level language you're using is the Domino's grammar, right?
Yes.
So compared with some C-like language, what's the key feature? I mean, what's the most specific grammars of Domino or in your language should be specific to the chip-based programming? Because say P4, right? P4 is a low-level language. It includes tables and it includes registers, and that means it's a low-level language because you have to specify what should be the read actions in the tables. That's okay. But for a high-level language, I mean, what's the difference between the say C and Domino? I mean, maybe it should have some features.
So for the future features of Domino and the C language, first of all, there's no pointer in Domino. Second, there's no loop, and we have this step. And then for Domino compiler, it will transform the Domino program into a lot of codelets, and the translated graph, you can regard it as similar to the what maybe I can show you here. So the translated Domino program, we will map it directly to this kind of two-dimensional PISA simulator, and then when it is allocated to the PISA simulator, we guess we can to deal with some register or to deal with some register table. These are it's very easy to deal with in this case. We have already solved which particular ARU will solve which particular functionality, and which particular output will pass to the next stage. That's what Domino compiler does.
Okay, yeah, thank you very much. Okay.
Yeah, thanks.
Any other questions?
Could you contrast the, this is Nate from Cornell, could you contrast the use of sketching in Domino with the synthesis that's done in Chipmunk? They seem somewhat similar, but I have a sense there's differences, but I'm possibly missing.
Oh, right. So yeah, so you're right. We use Sketch for both Domino and Chipmunk, but for Domino, it will do these two steps. The first of all, it will chop the program into several pieces, and well, we call each piece the codelet, and we will compile, or we will use Sketch to compile one particular codelet to a particular ARU used in programmable switches. But for Chipmunk, we will tell the user, okay, how many, what is the grid size you want? For example, you give a problem, and I give 3 stages and 2 ARUs per stage. And then I will let Sketch to find the functionality of each ARU, and including which output to pass to the next stage, which means I don't need to specify what's the grid size of. So Domino will chop it into pieces, but Chipmunk will let the Sketch to find the grid size for the whole problem. These are a little bit different.
I see. And the grid, I came late to the talk, so it's possible you addressed this already. So the grid size is constructed inductively in some kind of synthesis loop?
Yeah. So grid size, I mean, grid size can be tracked inductively by users. But if you specify the grid size, for example, I give the grid size 3x4, then Chipmunk will borrow Sketch's synthesis tool to try to find a configuration within the 3x4 grid size. Because intuitively, it's very obvious, well, if we specify the grid size to be 3x4, and maybe some of the ARUs will actually not be used, although it appears in the grid size. So we may see the actual ARU we use is 3x2, but we just waste 2 ARUs per stage.
I see.
Yeah, that's, yes.
One other high-level question, if I may.
Sure.
Someone else has one. Can you relay any experience with having Chipmunk synthesize some code that's somehow really surprising? Like either you didn't see how to implement the code, or the implementation that it generated was very different from what a human would write?
I mean, it usually happens because if you use some handcrafted rules for Domino, you may manually combine some codes to one codelet and to specify, okay, this kind of codelet should have specific functionality. But for Chipmunk, it will randomly search. It only takes care of the input. Well, I give a specific input and I give the specific output. I don't need to care about which parties go to the next stage, which party is used. So maybe we will give some really strange functionality for one particular ARU and strange functionality for the ARU in the next stage, but the combination of them become normal. So I mean, this usually happens.
Cool, yeah.
Yeah.
Xiangyu, maybe what Nate was asking was also like something concrete that you could say, you know, like, hey, here is something like very counterintuitive. Like if you remember any concrete examples, that might be nice. I think maybe that's, I don't know, at least I thought that's maybe what Nate was getting
I
at.
have a case where if you like have some if statement, so it will, for example, a very concrete case is it will set a specific stateful variable to 1. And then in Chipmunk, it may regard it as if this kind of, if condition A, it will set it as 1. If not condition A, it will also set it as 1. So which means this is still another way to express setting a very concrete stateful variable to 1, but it will use some strange if-else conditions to support this issue. Yeah, of course, there are more like strange results, but I mean, we've spent most of the time taking care of whether Chipmunk can generate the result or not. So we don't spend much time to see how strange Chipmunk generates the result.
Hey, this is Jen. I have a question also. So first of all, very nice talk, really interesting work. It seems like here the metric of success is, you know, whether the program can be made to fit. And I could imagine a different metric of success, which is more like how much of the program is able to fit, particularly if your goal was to take, you know, let's say the Domino program and run part of it in the data plane as much as possible, and then be willing to run, you know, let's say the rest of it on a general purpose machine. So if you had like, you know, a hybrid architecture like that, which might be suitable for, say, network function virtualization, where you're trying to do more sophisticated functionality than you might ever expect the data plane to be able to do alone. And so I'm just curious if you think similar techniques would be helpful if your goal was more of a program partitioning kind of problem rather than a program fit.
Yeah, so I don't know whether I understand fully of your question or not, but I guess it's really interesting. For me, your question is similar, like, first of all, it's very good if we can successfully compile a Domino program. If we cannot compile it fully, maybe we can compile it partially. Is it your question?
Yeah, exactly. I suppose your goal really is to run this particular Domino piece of code no matter what. And it would be perform better if more of it ran in the data plane, but you don't mind if a subset of packets or a subset of operations end up having to go up into general purpose software where there's some metric to define. You know, how happy are you to have something be, you know, maybe rare cases, you know, you might need to know something about the workload or the relative cost of the operations to do this, but where you really want it to work no matter what, and you're willing to let some part of it run in software rather than not run at all.
Yeah, I mean, this is very closely related to our recent talk, or at least my general idea for the next step for this particular project. So we can sync up, first of all, if it's fully compiled by Chipmunk, that's a good news. If it cannot, we think up some other ways to measure whether this can compile or not, which we also you call by partial compilation. First of all, if there are a lot of pack headers and a lot of persistent switch state, we can see whether we can compile some of them, like if we have 3 pack headers and 2 switch state, whether we can compile 2 out of 3 pack headers and 1 particular persistent switch state. The second case is we want to use min set solver to solve whether, for example, if our input space is 10-bit, whether we can successfully compile like 80% of this input space. And also we can sync up some ways to repair the Domino program, to simplify the Domino program until one point whether this Domino program now can get fully compiled with our architecture, but this program is a modified version, not the semantically equivalent. We also change some semantic, but we need to measure what's the difference between the updated program and the original program. We want to keep the semantic as close as possible with a slight change for it.
Cool, that sounds interesting. And I guess a related question is, in some cases, a program might create data structures whose size varies based on the workload. You know, a concrete example might be per flow state, where you don't know at compile time how much, let's say, register memory you're going to end up needing to run the program. I'm curious if you have thoughts about how to reason about that, or is that kind of question just sort of beyond the scope of what you're trying to do?
I mean, can you rephrase your question again? I'm not sure I fully get it.
Yeah, let's suppose you want to store in registers and say in a PISA switch.
Yeah.
A counter associated with each flow, like each 5 tuple. Let's say you want to count the number of packets you've seen for every 5 tuple. If you wrote a program like that, you would be struggling a bit because you don't know ahead of time how many flows you might end up seeing.
Right. Yeah.
And so knowing if the program fits is more of a runtime question in some ways than a compile time one, or at least it's workload dependent.
Yeah. So I mean, that's right. So I think it's more workload dependent, and I don't think Chipmunk has now already touched that part, which is a little bit beyond our research, this project research scope right now. But I mean, right now I don't have much idea about this one, but I think it's worth further thinking about it.
Cool, thanks.
Yeah, okay, thank you.
Jen, I think all of these are like fantastic questions for future work. I don't think we deal with any of the questions that you actually asked us. Like in particular, we do make a simplifying assumption that if you place a piece of compute, like an ALU in a stage, I mean, you actually have enough memory to hold all the match rules or like the things that you would actually store for that particular ALU stage. Like for example, if you're storing state per flow, and your stateful ALU is placed in a particular stage, you're kind of assuming that the state, you can actually store the state within that stage. So, but I think like it would be a really interesting question. Like even if you, so I mean, kind of even simplifying what you asked, like if you did actually know even statically, right, like without thinking about the workload, but even statically, if you knew the table sizes, like how much state you would want to store, I think we are still actually far even from achieving that goal, in the sense like you would actually need to kind of consider not just the functionality and the dependencies of the compute, but also the availability of memory of various sorts that you might actually need, along with the placement of the compute itself. So I think like we're even, I mean, I think there's kind of an interesting problem in combining potentially techniques from solving integer linear programs and synthesis. So, I mean, this is sort of an active thing that I think we really want to explore, actually, because I mean, even we definitely don't think that the solution is complete by only placing the compute. Like we really want to think about the memory as well and other resources, but we just don't have like a clear way or rather, like we sort of still need to think about a clear way of combining these different kinds of problems. Like one of which is sort of this, synthesis. Kind of, how do we respect dependencies? How do we keep all of the compute within the grid size? But the other one is almost like a bin packing problem, which kind of has this flavor of, do you actually have enough memory to place this box inside this bin, sort of a thing. So there's some work, I think, some sort of really interesting challenges in combining the two, and I think we should, kind of talk more about it for sure.
Yeah.
And also speaking to the other question that I had, like, sorry to hog the mic, I guess, but again, it's a really interesting question as to, how, like, what are the different kinds of hybrid implementations that you can consider. Speaking to your earlier question, like I could consider at least, think of at least 2 different ways to have a hybrid implementation. Like one is, so if you think about the domino, so let's say you have a piece of code, like a domino program, you extract all the dependencies from it, and you have this graph that represents all the dependencies. You could certainly think about running a subset of that graph on the fast path and a subset of the graph on a different machine, but that would have the property of, like every packet, you're sort of trying to say, okay, I'm cutting off the computation at some point, and the rest of the processing on a given packet has to happen on this other platform. Like that is one kind of partial execution that I can think of. The other kind of partial execution is thinking about how you would, like I think Xiangyu alluded to this as well, processing a subset of the packets on the fast path and processing a different subset of the packets on the slow path. And I think even there, I think there are interesting questions about, if you think that the synthesis is not actually going to hold. So in other words, like the synthesis problem really says, for all inputs, is the specification equal to the implementation? But you could restate the question as, can you maximize the number of inputs for which the specification and the implementation actually match up? And then, the question is, how do you efficiently detect, or sort of how do you efficiently solve that optimization problem? And also, how do you efficiently detect the fact that the input or the packet that's coming in actually belongs to one set or the other? So I think there are like interesting challenges all over the place. And yeah, like really, thanks a lot for asking these questions.
Right. And we are also thinking about if we know we cannot find a whole configuration to satisfy all the input, whether we can let our like generated code, the output as close to the Domino's output as possible. The like obvious thinking is about like some mean square error or whatever. I'm not sure whether, do you think this is meaningful or not? Like if like previously what it does is we can guarantee our compiled result will have the maximum error to be like 10, but maybe not quite accurate. I don't know whether this is useful or not.
I mean, I think that could be particularly for telemetry applications where you might be willing to tolerate a certain amount of accuracy, particularly if you know in advance what kind of bound there might be on it. I mean, another example is people will sometimes, let's say, try to have access control lists in an edge router. And if you can't fit all the ACLs, you might have a view of having, let's say, a liberal policy that you want to block as much of the traffic you're supposed to block as possible and never block something that's permissible. So you're leaving a tiny window of vulnerability if the adversary can figure out exactly which packets are going to sneak through the access control list erroneously, but that's better than having everything wide open, which would be your alternative. So I think imagine settings where errors could be okay in one direction because, like the security example would be one, and others where error in either direction could be okay as long as it's bounded because you're just trying to, I don't know, detect heavy hitters or, detect port scans or something, whereas you're just looking for something to be generally above a threshold and you're not necessarily so sensitive that it be precisely accurate.
I see. Okay. That sounds useful. Yeah.
That's great. Great set of questions, actually. Any other questions? Okay, I guess you could, if you have other questions after a while, you can certainly reach out to Xiangyu or Anirudh or myself. I mean, I think we'll be more than happy to chat. This has been really great. So thank you, Xiangyu, for the talk.
Okay,
we'll we'll let everyone get back to their day. Okay, thanks, guys.
Okay.
Bye-bye.
Thank you, everyone. Thank you.
Hey, thank you.